in the last class, we were at the tail end of the last class, we were discussing this aspect, which is what happens. I mean, we've earlier said that in a MOS transistor, the drain current is the effect, and the gate source or the source gate voltage, depending on whether it's a PMOS or an NMOS transistor, as the case may be. The gate drive is the cause, and the drain current is the effect. All right, and so what? But here we seem to be pumping or pulling current out of the drain of this transistor, right, and expecting that this gate voltage develop to whatever given by the formula, right. So the question is, clearly we seem to be contradicting ourselves. So where is the contradiction? That's what I wanted you to think about yesterday. How do we know that the voltage? I mean, how does the differential pair know that this is exactly the voltage it needs to give is exactly enough to support I2? Do you understand? Do you see the question, or I mean, do you see the problem, or is the problem obvious to you? That we have a problem is clear. I hope that much is clear. Correct? So all along we've been saying that you cannot simply pull current out of the drain and expect voltage at the source gate to develop magically, right? So what are we? I mean, but here we seem to be doing exactly that, which is evidently a contradiction of of what we've been saying in the past. So how do we resolve this? So okay, it is some current, yeah. So what? Yeah, I understand. We know how to get I2, correct? I mean, in other words, what I'm saying is that, okay, so if I asked you this question now, which is VDD I2, what is this voltage? What is the difference between this isolated circuit and this one? So what is the source gate voltage here? I take a PMOS transistor, pull a current I2 in the drain. What is the source gate voltage? This is the third time you're going through this, correct? All right. Now you're saying here it is magically when we put it in the circuit, how can it suddenly start working? All right. So let's assume that this current changes by some infinitesimal amount. Right, that I2 was supposed to be I2, but it's slightly less or more. What comment can you make? How does this transistor know that the current being pulled out has increased by? Okay, so therefore, what is the resolution of our seeming contradiction? So basically, the resolution of this thing is that the op amp is never meant to be operating in. The op amp is never meant to be operated without feedback. All right, because without feedback, for example, let us say if everything is perfect, let us assume that somehow this voltage is developed. Is developed such that magically somehow this current equals I2. Now, in reality, you can never get exactly I2, or even with temperature, maybe I2 changes a little bit, right? If the if the amplifier is operating open loop, this current remains I2. This current has increased slightly. So what comment can you make about the potential of that node? It goes down, eventually pushing this transistor into the triode region, where the gain of the operational amplifier is very small, right? So basically the open loop characteristic, if you plot the differential input voltage Vd, right, as and plot the output voltage Vo, okay, there will be a positive saturation limit, right. That's when this node voltage goes up. The highest this can go in this particular case, what is the highest ever that voltage can go to? What is the highest potential this that gate can go to? Approximately, very approximately. VDD minus of which transistor? Where is M6, man? Yeah, the gate of M6, what is the highest it can go to? Delta V of which transistor? Okay, so alright. So the highest this can ever go to is, I mean, it's VDD minus the drop across that transistor, and if you want to make it very approximate, the highest this can ever go to is VDD, correct. So what is the highest this can go to? VDD minus VT minus something. I mean, so a good approximation is basically just say, I mean, VDD minus VT is good enough, right? Okay, so and what is the lowest this voltage can go to? Okay, if this node has to go low, what must happen here? This should be in triode. So this voltage will be very small. So what will happen to M6 therefore? If the gate of M6 is close to ground, what will happen to M6? It will go into cutoff. If this goes into cutoff, what region of operation will M7 operate in? Linear region. So what will this voltage be? What is the current flowing through M7 therefore? If M6 is gone into cutoff, what will M7 do? What is the current in M6? 0. What is the current in M7 therefore? 0. What is the gate source voltage of M7? Where is M7's gate coming from? From some mirror, right? So what region is M7 operating in? So what will be the voltage across the drain source? 0. So what will be the minimum voltage? 0. Is this clear? Okay. So the voltage, the output will look like something like this. When VD is about approximately 0, you will have a huge gain, and then it goes like that. When VD is infinitesimally greater than 0, then what happens? The input differential pair steers more current one way and less current the other, and this is what happens, correct? If more current flows here and less current flows here, which is what will happen when Vi is slightly positive, then what happens? More current is flowing here, less current is flowing here, and therefore this node voltage will attempt to go up and therefore cut I2 off. If I2 gets cut off, this voltage will go to, if I2 is off, I mean if that transistor is off, then I2 is 0. So what comment can you make about that node potential? 0. If this is 0, then M6 is off. If M6 is off, M7 will be in the triode region and the voltage will be 0. If Vi is infinitesimally negative, then what happens? Less current is here, more current is there, less current is there. What comment can you make about this node? It will keep reducing, right? And this transistor will be in the PMOS transistor will be in the gate voltage is following down, so it is attempting to push more current. So this node voltage will go up, okay, eventually pushing this transistor into the PMOS transistor into the triode region. So this M6 will basically have a potential which is close to VDD, the gate. So the output voltage will go to VDD minus, roughly VDD minus VT. Is this clear? So and in the middle, finally the voltage for infinitesimally small negative VDD was Vi was 0, For infinitesimally positive stuff, it is VDD minus VT. In the middle, it must, I mean, it can't go there and come this way, no, it has to go this way, correct? Okay. So, you can see that if there is any small change somewhere, this, you know, for example, two transistors are mismatched and so on, basically this curve will shift to the left or the right. Okay. So, when you apply, I mean, you should never take a high gain op amp, you know, even though the equation says the output is A times V1 minus V2, where A tends to infinity, right. You should go and put V1 equal to V2, therefore it is 0, V1 minus V2 is 0, and therefore the output must be 0, okay. That is not correct, because in reality what happens is that the output VO is some A times V1 minus V2, right, and this is only true in this region, alright. In reality what it will be is, even in that region it will be of the form V1 minus V2 minus some offset, because of non-idealities inside the op amp. Most of the time this is because of mismatch in thresholds and so on, right. And this is only true, you know, provided this quantity is less than VDD and greater than 0. So, in other words, the output of the op amp can be modeled as a straight line only over a extremely small window of input voltages, right, okay. And why extremely small? That is because the gain of the op amp is very, very large, alright. I mean, if you have you know, a million as the gain, and if V1 minus V2 is 1 millivolt, right, the expression is telling you that the output is going to be 1000 volts, but you would be completely mistaken if you go and put 1 millivolt and expect to see 1000 volts at the output of the op amp, right. It will saturate to VDD or ground depending on the polarity of, and even if you put V1 equal to V2 equal to 0, V1 minus V2 equal to 0, you still have this unknown offset term, which will drive the op amp either into positive saturation or negative saturation if you operate it open loop, okay. If you actually were paying attention, you would have noticed that if you just, you know, just power on an op amp, and it seems like the output should be, and even if you connect the two inputs, short the two inputs together and connect them to a some potential, you should have found that the output is either plus or minus VDD, okay. So, then we went and calculated the gate source voltage of this transistor using the formula. The assumption is that, what is the assumption? The assumption is that all transistors are operating in saturation, which is only possible when the differential input is very small, which can only be ensured by a negative feedback, alright. So, let me take an example, which was the inverting input of the op amp, the left side. So, let us say we put 2.5 volts here, which is VDD by 2, and then we close the loop as a voltage follower, correct. Now, let us say, I mean, there is you know, yesterday we went and calculated the quiescent voltage here, it is 2.5 plus 1.2 is some 3.7 volts, okay, alright. Now, let us say I deliberately suddenly increase this current by small amount. So, what will happen to this potential? What will it tend to fall down or go up? Fall down. So, it will tend to fall down. If this falls down, what comment can you make about that voltage? If the input, that stage, the third stage is basically a common, it will tend to fall. If this tends to fall, this is the same node, so that falls. If that falls, what comment can you make about that guy? Falls down or goes up? Falls down, alright. if that node falls down, what is happening to the source gate voltage of that transistor? It's increasing, doing what? Therefore, increasing the current so as to keep this node potential from falling. All right. So, there is indeed negative feedback. It is not, I mean, only but there is negative feedback only when you close the loop, when the op amp is enclosed inside a negative feedback loop. You understand? Okay. This is a subtle thing that a lot of textbooks don't even bother to talk about, right? And they will do the analysis just like we did. This was in saturation, all these voltages. That's perfectly all correct, provided the op amp is sitting inside a negative feedback. All right. So, all right. So that completes our discussion on the DC properties of our op amp.